So we will be talking about radian measures of angles, so that other way of measuring angles, and other ways of writing linear equations today. So a little bit of vocabulary that we need as we get started. We need to talk about what a radian is. A radian is another way of measuring angles. All angles are just a way of measuring how much we are rotating around the circle. So a radian is going to be when our arc length is the same as the radius. So when we have gone 1 radian around the circle, that means that the arc length is the same as the radius. That is 1, and at that point, the measure of the angle is 1 radian. Just like with any angles that we've talked about, it does not matter where we measure that angle. It doesn't matter if we're talking about this teeny tiny little piece of a small circle, or circle that's even bigger, or somewhere in between. All of those that I have outlined in blue would have a measure in radians of 1 radian. It's a little bit less than 60 degrees. If this green curve had been a straight line that was also R, we'd have an equilateral triangle. But because it's curved, it's squished down a little bit lower. It's 57 point something in degrees. You aren't responsible for knowing that, but just kind of for a little bit of a frame of reference. It's when the arc length is the same as the radius. I'm going to repeat that same picture here, just without all of the circles inside of circles. So if I went all the way around a circle with radius of R, the arc length would be the circumference, right? And so it would be 2 pi r. So if R is 1 radian, when I've gone 2 pi r around there, I've gone 2 pi radians. Does that make sense to everybody? So all the way around the circle is 2 pi when we talk about radian measures. So if I only go halfway around the circle, how far have I gone in radians? What, Anna? 1 pi. So let's start filling in our that unit circle that I had you skip on the front page. Let's fill that in with our radian measures. If we are right here, we are at 0 radians. And we also said that was the same if we went all the way around, 2 pi radians. And you just told me if it's 2 pi all the way around and we only go halfway, then we have gone pi radians. Everything else about radians is fractions. So whether fractions are your favorite thing or not, that's all that there is to radians, to try to figure that out. So if the top half of the circle is 1 pi, what if I only go up here to the top of the unit circle? That's going to be a half pi, or pi over 2. And that means if I go down here, I've gone pi and another half pi. So this is 1.5 pi, or 3 pi over 2, halfway between 1 and 2 pi. Everybody good with those? Okay, if it's pi over 2 up to the top of the unit circle, what if I only go right here? What, Avery? Pi over 4. So if I think about these spokes, along with these 2 original ones, I've divided that top half into 4 equal pieces: 1/4, 2/4, 3/4, 4/4 when I'm back at pi, 5/4, 6/4 is the same as 3 pi over 2, and 7/4. So those fractions all make sense to everybody, right? Okay, I'm going to change colors so I can talk about a different fraction now. Let's suppose I'm still going to keep this axis in here. And let's talk about here and here. So only the parts that are either solid or partially blue right now. The top half of the circle is pi. How many equal pieces do those blue lines divide the top half into? 3, so each one of them is a third. So pi over 3, 2 pi over 3, and then 3 pi over 3 has us back at pi. If we keep going, 4/3 pi, 5/3 pi, and 6/3 pi has us back at the same place as 2 pi. Just fractions with pi thrown on afterwards. Okay, we've got a few left to do. So if this was 1/3, if I talk about this, I've cut that 1/3 into 2 equal pieces, right? What is half of a third? A sixth. So this is pi over 6. So if I divide that top half into 6 equal pieces so that each one is a sixth, I'm now talking about those lines that are either solid or partially green. So 1/6, 2/6 is the same as pi over 3. 3/6 is pi over 2. 4/6 is 2/3. So this one will be 5/6, or 1/6 less than the whole pi. And 6/6 has me back there at pi. I can continue with this bottom section as well. So 6/6, 7/6, 8/6 was 4/3, 9/6 was 3/2, 10/6, that's 5/3, and so this one is 11 pi over 6, and then just need one more 6 to make 2 pi. And those are your radian measures for the unit circle. So we've purposely not written degrees on your sine and cosine and tangent circles, because regardless of whether you get there with radians or degrees, if you are right here, then your sine is √3/2 and your cosine is 1/2, and so on around the unit circle. Let's also do the radians in the negative direction. So turn over on the back, one of those you haven't used yet. It's going to be the very same fractions, except I'm going to go the opposite direction. So I'll let you guys copy these. So now I'm going down from the x-axis, up pi over 6, pi over 4, pi over 3. So the numbers go the reverse direction, and then you put a minus sign in front of each of them just to say that you are going in the negative direction. And once you finish that, we'll start adding some things in on the formula list, but keep that page out because it's going to help you with some of the problems we will be evaluating. So does this make sense to everybody? I know you don't have it memorized yet, but it's just fractions. You can figure this out just by thinking about your fractions, just like with degrees. A positive angle measure means you go counterclockwise. A negative angle measure means you go clockwise, starting from the positive x-axis. Nothing has changed in that on that part just because we're using radian measures. Okay, so 180 degrees is how much in radians? Half of the circle is 180 degrees, or what in radians? Pi. So if we need to convert in a problem between degrees and radians, 180 degrees is the very same thing as pi in radians. So we can do our unit multipliers since those amounts are equal to each other. It does not matter which one's in the numerator and which one's in the denominator. Except we never actually write them like that because we never actually label radians. So we only use that as 180 degrees over pi or pi over 180 degrees, and we never actually mess with writing out radians. The other thing that means, if no units are on an angle measure, it means radians. So be sure that when it's degrees, you do not accidentally forget to label it degrees. Because 1 degree and 1 radian are not the same thing. 1 degree is very, very small, but if you leave that degree sign off, it means 1 radian, which is almost 60 degrees. Not the same as 1 degree. Now, in general, the only time that you will actually be converting is if the directions say for you to convert. Most of the time, I do not want you to convert if it's just saying what is the cosine of pi over 6. I don't want you to waste your time converting. It'll take too long. I want you just to learn in radians. That means I'm here on the unit circle. So the cosine when I am there is. The sine when I am there is. But let's just practice so that we can. This one is in radians since it's got a pi in there and it does not say degrees. So if I want to change it to degrees, I need to multiply by the unit multiplier that will have degrees in the numerator and the radians in the denominator. The pi's cancel out. What's a fourth of 180? 45. Look at those 2 unit circles that you have side by side with the angle measures on them. Are pi over 4 and 45 degrees in the same location? So it worked. Okay, let's try 135 degrees. If we want to change that to radians, we need to divide by the degrees so that they will cancel out. So we need the 180 degrees in the denominator, pi in the numerator, degrees cancel, and let's see, 135 over 180, I think I can divide them both by 45 and get 3 pi over 4. Look at your unit circles. Are 135 degrees and 3 pi over 4 in the same position? Should be if you copied it out right. And one last one of these. 11 pi over 6. That is in radians. So if we want to convert, we need the radians down in the denominator to cancel out. We want to end up with degrees, so we have the 180 degrees in the numerator. The pi's cancel. 6 goes into 180 30 times. 11 times 30 is 330. Are 330 degrees and 11 pi over 6 in the same position? So those conversions all worked, which they should. We could have used 360 over 2 pi and 2 pi over 360 for the unit multiplier. We just simply reduced it. That's why we've got the 180 and the pi. So any questions with that part? Okay, next formula is this one down here. It's another arc length formula. If we are given an angle's measure in radians, or if we need to have the arc length with that in it for some reason, all we had to do is take the radian measure times r. We will get the very same result if we had that angle measure in degrees and we did x degrees out of 360 degrees times 2 pi r. We will get the very, very same thing. And I'll show you that on the next example. Where this formula is really, really nice is when you have the occasional problem where they give you the measure in radians. It's a lot shorter just to take whatever that is times r and not convert it to degrees and then divide that by 360 and then times 2 pi r. Everybody good with that? Okay, the kind of problems where we will be using this, if we are talking about my cross-country people, this is your afternoon practice run down to the equator and back. Just for your afternoon run, easy, right, Kay? Yeah, I'm with you on that. Not. So the curvature of the Earth would come into play if you were going that far, right? Because we'd be going along a curved surface. We might not be aware of it every single step, but over the whole journey, it would certainly be curved. If I'm just talking about how tall is a tree out there, is that far enough away that the curvature of the Earth matters? And the tree itself is usually pretty straight. It's usually not growing in a curved shape just because it's going around the globe or something. Those problems will still do right triangle trig. But when we're talking around the curved surface of the globe, we're talking arc length. So our short formula is that the arc length is the radian measure times r. That's going to give us exactly the same result as if we use the old formula, x out of 360 times 2 pi r. And you're going to see in a moment that we do get exactly the same thing. If I used this formula, which I might as well since this one is given to me in degrees and not radians, I would take the 39.642 degrees over the 360 degrees times 2 times pi times the radius. If I have this and I want the radian measure, I need to take my degrees, 39.642 degrees, and now I need to convert it to radians so that I can put it into this formula. My unit multiplier for that is 180 degrees underneath pi, and then I've got times r. Well, if I used my old formula and took the 2 into 360, does that not look like exactly the same formula? So you can do these either way, but if they ever give it to you in radians, definitely use the one on the left. So here's where I'm going to need your calculator help. So let's see, I need to plug in and evaluate. And so let's see, what do they tell me? 7920, so is that good? Is that what I need to plug in? I'm glad I'm seeing some heads shaking no. Why is that not quite the right thing to plug in? That's the diameter, so to get the radius, I need to divide by 2. So you guys plug that in and tell me how long that cross-country practice run today is going to be. That I am definitely not participating in. I would not be participating even if it's 1,000th of the answer that you're getting. Are we getting to an answer there? Sophia, what'd you come up with? So questions for that much. Okay, let's move on to some other kinds of problems. You will have a lot like this where you are asked, you've been doing these with degrees, positive and negative direction. It's going to be the very, very same thing when we are doing these. This is why I wanted to go ahead and get the negative radians up there as well as the positive radians for you. This is the kind of problem I'm talking about. I do not want you to convert, and I will not give full credit if you convert from radians to degrees on these. I want you to get used to, in radians, where am I on the unit circle? What is the cosine there? What is the tangent there? And plug in. Otherwise, your homework is going to take longer than it is meant to take. And when it's a test time, you're not going to have enough time to convert everything to degrees and then figure it out. So I want you just to get into the habit from the beginning. Where on the unit circle are we? So just like with degrees, we could go around more than once and we just keep on going. The same thing can happen with radians. So we're going to go in the negative direction, so clockwise. I'm going to start out going down and around. And since it's in sixths, I find it helpful to count by 6 pi over 6 until I get close to that. So In the negative direction, 6 pi over 6 puts me over on that axis going to the left. 12 pi over 6 brings me back where I started. 18 pi over 6, I'm back to the left. 24 pi over 6, I'm back to the positive x-axis. And then I need to go a little bit more. So I need to go pi over 6 more. So that means I am going to be, that looks too much like 45. Let me make it a little bit squishier. That means I am going to be here on my unit circle. So now I need to think about the cosine when I am there. Normally I would have 1, 2, square root of 3. But to make it on the unit circle, I want the hypotenuse to be 1, so I'm going to divide everything by 2. This one is my negative 1, since it is my vertical piece. Cosine is going to be adjacent over hypotenuse, adjacent over 1. So what's my adjacent side, Casey? So that's the process I want you to use when it's in radians. Yes, Anna. Draw something of where you are, because that's how you're figuring it out. But don't mess with writing down that that is 330 degrees or that is negative 30 degrees. Okay, minus 2 times. Okay, 4 pi over 3. That's less than 1 time around. So let's see. I've gone pi, so I've gotten over to the negative x-axis. 1/3 more. That brings me down in the third quadrant. So that means I am right down here. If I draw my triangle, normally 1, 2, square root of 3, divide everything by 2. Both of these are negatives. So now, if I am taking the tangent of this angle, opposite over adjacent, negative root 3 over 2 over negative a half, same as negative root 3 over negative 1. So positive root 3. These are both root 3s, so they are like terms and must be combined. So I need a common denominator. So I have, final answer is going to be over 2. 1 root 3 minus 4 root 3 is negative 3 root 3. Let's do one more of these, and then we'll move on to linear equations, different forms of them. So 4 times whatever the sine of pi over 4 is. So I want everybody with your hand, show me where on the unit circle is pi over 4 going to be. Everybody. Okay, so first quadrant, halfway up towards the y-axis. If we are right there, sine of that is going to be opposite over hypotenuse. Normally it was 1, 1 root 2, but if I make that be a 1 for the unit circle, opposite over hypotenuse, so opposite over 1, so it's going to be that vertical side over 1. What's that going to be when I rationalize the denominator? What is the sine of pi over 4? Come on, somebody can tell me. Thanks. What's it going to be? Root 2 over 2. So that one simplifies to 2 root 2. Okay, this time negative direction. And again, everybody point with your hand. If we're going in the negative direction, where will we stop for pi over 3? Okay, good job. We're ending up in this fourth quadrant down here. So 1, 2, root 3, divide by 2's, and this is our negative 1 right here. So what is my sine when I am at that angle? What will we get, Jack? So a negative root 3 over 2, and these are not like terms, so we can just leave it like that. One's a square root of 2 and one's a square root of 3. So it takes some getting used to, but you get the idea of the process. Any questions with that much? Okay, let's change gears then, and we will talk about lines. What's your favorite form of a linear equation? Y equals mx plus b, which is slope-intercept. We've had one other one that we've used a little bit this year. Point slope. Y minus the y coordinate is the slope times x minus the x coordinate. So if it's some other point we know, and we also know the slope, but we don't know the y-intercept, we can just plug into this, or we can plug the coordinates in and solve for b. Other forms of that we're going to start working with. General. What you have to do with a general one is you must get it equal to 0. You must start with x, and then y, and then a constant. Constant might be 0. Depending on if it's a horizontal or a vertical line, a or b might be 0. No fractions. Is what this means. A, B, and C must be integers. And you can't start with negative. So you just multiply to clear the fractions if you have fractions. And if whatever's by x is a negative, you just change all of the signs so that the x one starts with a positive. That is general. Double-intercept is interesting and nice and useful. If you know both x and y-intercepts, you can write down the equation x over whatever positive or negative number for where the line crosses the x-axis. This must be a plus right here. Y over whatever your y-intercept is. B is still the y-intercept, just like it is in the slope-intercept form. But any negatives go in the denominator. And then that one is equal to 1. And one last one, which really is if you had 2 points, and you say you want to do this, you have to first use the 2 points to figure out the slope, and then use this. So that is called the 2-point form. It's still y minus y1 equals m times x minus x1. It's just they didn't bother to give you the slope, so you have to use both points to get the slope and pick either point you like to plug in. And then we'll run through a couple of quick examples with those, and then we'll do that quiz. Is it okay for me to go on? Okay, so use point slope. So that means I know a point and I know m. So that's the y minus y1 equals m times x minus x1. To get the equation of a line with a slope of -1/4, so we're going to put that in here. The point that we know, x is 2, so this becomes x minus 2. And this will be y minus -4, so y plus 4. Everybody good with that? We want to get to general form. That means we want to get it to ax plus by plus c equals 0, no fractions, a is positive. So let's see, what do we need to do? Let's distribute that -1/4 so we don't get ourselves mixed up with that. So we have -1/4 x plus 1/2. So far so good? And let's see, at some point I'm going to need to put, I'll go ahead and leave the y plus 4 like that. I need to get everything on the right-hand side, and I need to get rid of fractions. So do you want to get rid of the fractions first? How do we get rid of fractions? What do I need to multiply everything by? Least common denominator, so I can multiply by 4. So I have 4y plus 16 equals minus x plus 2. Now let's get everything on the left so that it's all equal to 0. So if I add x, I have 1x over here. I'll keep my 4y. I need to subtract 2, so I have plus 14 equals 0. Do I have any fractions? Do I have x then y then constant equals 0? And do I start with a positive? And I'm good. And let's do one with double intercept, just since that is kind of the most different one. So we want to get this to x over the x-intercept plus y over the y-intercept equals 1. So there are two ways that I can do this. I can say 4x minus y equals negative 16. I want to have a 1 over there. So what do I divide by to get 1? So I'm going to divide by negative 16. So that means I have x over negative 4 plus y over 16 equals 1. So my x-intercept is negative 4, 0. My y-intercept is, 0, 16. So that is one way that I can do that. The other way that I can do it is if x is 0, I'm talking about my y-intercept. So I can say if x is 0, I have 0 minus y plus 16 equals 0, just putting 0 in for that x. So that means y is 16. The y-intercept. So that is what b will be. Then I can reverse it, and I can say if y is 0, then I'm talking about my x-intercept. So if I put a 0 in here, I have 4x equals negative 16. So x equals negative 4, so that is my x-intercept. And then I can plug those in. X over my x-intercept plus y over my y-intercept equals 1. Any questions with that? Okay, then that ends our notes for today.